Hi everyone. So this is the first part of uh, the Transformers recitation, where we will code from scratch. So um, this one will be more about the basics of Transformers and how we code it, um, so that for the future recitations, um, we can just go over what researchers in the community have done and what the architectures, how they change the architectures and their use cases in different fields such as vision and natural language. Although once this is, uh, so one of the cool things about transformers are that they are data agnostic in terms of it could be vision, it could be different parts of, uh, it could be the data could be from camera, it could be from lidar, it could be from many things. It could also be multimodal. So uh, yeah, that's the cool part of, and this really stems from the fact that you have these self and cross attention blocks, so you could join the information. Uh, yeah, with that, let's begin. So before we jump into the code, I wanted to um, go over some things. So this is the transformer that professor has been through, that Abu has been through in, in the last lecture. And um, I'll not go into the detail of it because that's what happened in the lecture. I will be going into the implementation of how you implement each part, and then link it together. Um, yeah, so I'll be coding that while on this meeting. So I'll be coding some part of it. I'll just jump through some other parts of it because they'll either be repeating whatever has happened before, or they'll be easy for you guys to implement. So some intricacies to get out of the way, because it's easier that way. So I'll not again be going into the detail of this because uh, I guess in the poll it was quite clear that people don't want to go into the intricacies, uh, which is understandable. So positional encodings and self-attention, cross-attention. This has we've been through multiple times in the lecture, but in case you don't remember or you're not sure about it, um, this is the easiest way of understanding. So key and value will always be from the same source, but your query can be from different sources. So if your query is from the same source as your key and value, it's self-attention. And if your query is from a different source, it's cross-attention. That's it. That's what you, that's not always true, but in most cases it's true, and that's all you need. So and the reason for that is I'll explain it during uh, the coding session also, but just to get it out of the way, um, the reason for that is because you effectively trying to find queries which are closest to the sum key, and you're taking that projection, adding it to the value to find basically the value which is closest to the key, um, which is closest to the query. And that's basically the attention code as well, which is this one. So you have some query, find the projection of the query closest to the key, and then you use that to get the final value using the as a weighted sum of these. We'll come to that. So that's one part. Now let's go to the positional encoding part. So it's basically your inputs. You get an input embedding, and then you add it to the position encoder. How does that happen? Well, your inputs, let's consider your input to be a sentence, and in that sentence you'll have words. Those words could be part of some vocabulary, and in that vocabulary uh, you have the indices, or you can call them, well, you can think of them as their numbers. So each word will have some number, and that you use that to create random initial embeddings which will encode the information about the word. You add those initial embeddings or those embeddings which we will train over time also. We will use those embeddings and add the position part to it, which is what is being done here. And the way we do it is we have these exponential sine and cosine terms which depend on the position, and so and the interesting part is they're made in such a way that no two words would be unique because of the way this sum is being added. That's all you need to know. It makes it unique, the position of each word. Yes, so that's one part. Okay, the other part would be masking. So if you've attended both Professor Nabu's lecture, or if you read the slides, you would know that what you're doing is next sentence prediction, next word prediction. Sorry. So for that, you basically need to mask the input so that you only see the words which are which have already been predicted till now. So this y2 only attends to x1 and x2, y3 will only attend to x1, x2, x3, and when you reach the last word, you would have seen the words before it. This is to prevent the network from seeing the next word, because it could definitely just see the next word and predict what it is, right? So if you see x4, it would have predicted x4 directly. But for the encoder block, that's not true. So let's look at the architecture. This is the same from the this is the same as the one that you've seen in the paper. So you get your inputs, you make input embeddings, add the positional encodings, you pass it on. Now here, this is the encoder block. So in the encoder block, you have this first block, which is self-attention. You add you have a skip, connect, and normalization, followed by a feed-forward network, and again one more skip plus normalization. The thing to note here is the fact that this block, it could be multiple such blocks stacked together. That's where this nx comes, which is you could have multiple such blocks creating the final encoder. So the way we will be coding it is we'll create each module, we link those modules to make one encoder block, and then we would create the encoder finally by using these encoder blocks. Now looking at the decoder, it's quite similar in the notion that once you get the input, you have a self-attention, but it's masked self-attention. So your words are only attending to the words that they've already seen, and then you use that. My apologies. I guess I was on this slide. Yeah, and then you use that to basically get the queries. But this is the part which gets interesting. If you see this part, it's actually this part. It's my bad, sorry. So it's actually the same, these two. The only difference being the keys, the way the keys and values, key value and the query are being passed. So in this case, the key value and query were the same. So this was a self-attention block, while this is a cross-attention block, where the queries are coming from the decoder that we already have written, and then key and value are coming from the encoder. So this forms one decoder block, and we'll have n such decoder blocks to create one decoder. I hope that makes it clear. Okay, I won't bore you guys anymore. Let's jump into the code. So, okay, we'll begin by writing the self-attention block. So, okay, You please feel free to speed it up if you feel that I'm going slow. This is more for me to write the code, because I feel if one is writing, there are some small parts which you think you know, but till the time you really don't write it down, you don't quite understand. That's how I like to code. And one of the videos that I'm referring to here is one where um, actually a couple of them are where the people actually code it out, and that made more sense to me. So that's how I'll be doing. Not all of it will be coded. I'll be skipping through some parts. I'll be using those directly. So okay, so I'm creating the self-attention block, which is uh, this part here, right? And then it will be multi-headed. So you have your values and keys and queries coming in, and it will be multi-headed. So we look at that as well. And yeah, I'll be skipping through the visuals also in between, so that it's easier to understand what part of the code it is. Okay, need to call. Okay, so you have your embedding size. And then you have your heads. Now the thing to note here is that the input embeddings will be split into equal parts. Okay, and the reason that happens is um, these embeddings, you'll be passing them to the heads. Maybe it'll be easier. Yeah. So you have these heads. You'll be splitting these into parts, um, into equal parts, and then you'll be concatenating it again so that it's the same shape. So um, that's why I'll split the embeddings that I've got. And because for this part, it's self-attention, I know for a fact that they'll be the same size. So now, one more thing to note here is we want to make sure that the embed size is actually divisible by heads, because otherwise when you concatenate it, this won't work. So we'll have this assert statement here. Which basically says that if the embedding size means to be divisible by heads, okay. Now moving on, we'll be creating some linear layers, which is just so that which is not really clear, but after the inputs. So before I pass it directly to the um, network, I actually have this linear loop. So I get this, I convert it into linear, and then I split it. Yes, so actually we'll go to the part when we skip it, but there's a linear layer before you pass it on. So let's look at that. So this is the embedding size, and again, to the embedding size. So you pass it to the linear and then you split it. I'm just going to copy this because it's self-attention, all of it is same. So okay, now this is the query. However, this is the output, and again, this will also be the same size because of, well, not necessarily, it'll just be the same size in this case. So let's move forward. So here you'll be passing your values, your keys, query, and the mask. The mask here, if you're paying attention, you would, pun not intended, you would know that the values, if you're using it just for the encoder block, it doesn't really matter because we won't be using a mask. But the cool thing about this is that this block, along with the feed forward network, the structure is actually what we need in the decoder as well. So this structure is what we need in the decoder as well. So that's why we will be looking at the mask also, so that we can reuse this code again. And we need the mask for next word prediction. Okay. What I'm doing here is trying to get the length of each input, and that would be clear later why we would need it, because okay. So now we need to, in order of what comes in the block, let's look at the block. So you get the values, your keys, and the queries, you then pass them to the linear, and then you pass it to the multi-head attention. What happens in the multi-head attention is you have these query and the query and key coming in. You do a matrix multiply. We'll be doing it differently, but you can do a BMM. Then you scale it, which is this. You put a mask if you want to, and then you do the softmax, and then again a matrix multiply between this projected term and the value. That's your attention. You have multiple of those because it's a multi-head attention, and the inputs of those were split. So let's look at that. Okay, so this. So I'm passing it through the, so I'm passing it through the linear layers. Okay. Now we will split the embeddings before passing it to the multi-head attention. So we'll reshape the so you have the batch size, the value length. This is one of the reasons why we need the length, because we want to reshape it in where the length doesn't change, but your embeddings, the way the embeddings are represented, change. So you become self.heads and self.head dimension. So it was before it was self.head dimension times self of heads, but now we have split it so that we pass it to the so that we can pass it to the cross attention. These what we should and these and then self.heads. Then you do the same thing for queries as well. So you have queries, reshape, and then again batch size, query. Feel free to skip if you if you if you understood this already. I just find it useful to still write down everything. So now that we have this, so we have split it, we have split it after the linear. Now we'll be going into the multi-head part, which is basically this. So I'll just add some comments here so that it's easier. Okay. So this, the way the scaled, the matrix multiply is done can be done multiple ways. You can do BMM or you could do tensor dot, matmul, but we'll be using einsum. And I'll try to give a small introduction to einsum here, but if not, you can search online. There's a great video. I can link it as well. And I believe, I mean, it's as long as you get to the initial barrier, einsum I believe is a lot easier to implement, and it's one of the easiest to not make a mistake in because of the way you actually code. I'll not waste any more time here. I'll just explain what is being done so that it's easier for you. And this part actually would be useful for homework 4 as well, because you'll be implementing attention there again. The attention, the way the attention is calculated will be the same. It's just, and you could also use a multi-head attention block in homework 4. So this part actually is quite useful for homework 4 as well. Okay, so we'll term some energy. Okay, so we know the shapes of both the key and the query. So the first thing we're actually doing is this matrix multiplication between query and key. And the way we, maybe I could just keep it like this. Yeah, it's a little short, but I think it should still be visible. So the first thing you need is this. And the way you would do it is you have, you know the shapes. So for query, let's call the shape n, which is for the batch size, q for the query length, h for the number of heads, and d for the dimension. But this heads and dimension would be the same for both the query and the key. We're doing a matrix multiplication between the query and the key. So let's add the key. The key dimension again n, key length, head, and dimension. And now, what are you doing here? Well, let's make it big again. What are we doing here? We're doing this initial part, wherein we're doing a dot product, or a, let's not call it dot product, let's call it an inner product of the query and the key. So you're doing it across the last dimension, whereas you're doing it across the embeddings. So you'll basically be removing that term away, right? So let's look at this. So it becomes n, h, q, k, which is, you have the number of heads, so the batch size, the number of heads, the query length, and the key length. What this is giving, if you look at it closely, is for every query length, you will have something corresponding to each key length. So for every element in the query, you would have something in the key, and that is what you would be multiplying with the value as well. So you'll basically be taking a weighted sum of each part of the value for each query. And so now for yes, so this is the query dimension, which is this. This is the keys dimension, which is this. And then you basically multiply it such that you remove the last two dimension, and what you get finally is you get your batch size, your number of heads, and for each query in each head, you'll get k values, and though you'll be using those to get a weighted sum of the values. Okay, so if mask is not none, so this is for the case where you'll be using the same block in the decoder. So we're looking at next word prediction, so we don't want to be looking at words which are in the future. So in this case, your energy is actually energy dot mask fill. This will be useful for homework 4 as well, this mask filling. Okay, so and what this is doing basically is, for the parts where you have a mask, you're filling it with very small values. So, and you could do it differently, really. So let me show you the mask part. What it's doing is, for the parts that you have, that is to be empty, so that you don't look at the other parts. You actually make the value to be really small, so that when it does multiply with the raw tension weights, those parts are reduced to 0, or in this case, a very small number. Okay. Now I'll just add some comments so that it's easier again to understand. Yeah. So now that we're done with this part. So now we'll focus on this last part and adding it to the values. So let's look at that. So now we need to divide it by the square root length, which is the scaling, and then we need to softmax it. So the weights are between 0 to 1, which is what you'll be multiplying with the values of. And for each head, we have each element paying attention to each part in the key. So we have for each head, you have for each element, you have some, which is the query length, you have some part which is attending to each of the query key length elements. And the reason why we are doing it is we want to map each key, each part in the query to the value. So so you basically made this part, the last part, you softmaxed over the last part, and you have that between 0 and 1. And that will help us with the weighted sum eventually. So another part. This is the last part. So we've done the matrix multiplication. We've now scaled it, and yeah, apologies. So we've now scaled that, and we'll add the mask if necessary, which we did already. And then we added the softmax, which is what we did just now, which is we made the dimensions across the last dimension, which is where the key values were, to lie between 0 to 1. And now we'll be doing a matrix multiplication of this final thing with the value, so that you get something which is in the value space again. So let's look at that. So you have a torch.time sum again. And what was the input? The input is the attention again, which we already know the shapes of. So it's basically for each head, for one batch size for each head. For each query length, you actually have the parts that it's paying attention to across all the key lengths. And let's call that dimension L. And this is value. So notice the way the value was, which is N value length, the heads and the head dimension. So it's the same thing. So it's N LHD. The L would be the same because key and value are the same, and the heads and the value dimension. Now what we want is we want for this part, this L length, to attend to each part in the value. So that is why we would be removing this L basically, because each each key part is being mapped to some part in the value, and you want a weighted sum of that for your query. So what you effectively get is you get for each query element you get heads and heads, and for each head you have some dimension, and this is useful because we'll be concatenating that to finally get into the same dimension space as into the same space as the values. So now let's combine, which is right. So as I said, we combining these two. Let's do once this is done, let's do a walkthrough of this again, so that it's quite clear what has happened. So now this final output, we'll be passing it through the final linear layer. So And this doesn't really modify the shape. So we have the same shape as before. And then you just return out. Let's look at this again so it's completely clear. What you have is you have your query key coming in, and then you do a basically do a inner product to find the projection of this query in the key space, right? And then you scale it and a mask if it's necessary. So only when you're looking at it in the decoder block, you would mask it so that you're only looking at words that are preceding. And once you do that, you do a softmax along the last dimension, because you want the final weighting to be a weighted sum, and in that weighted sum you want the weights to lie between 0 to 1, and their sum to go up to 1. And that's where this term comes in. Now you use that to basically get a weighted sum of the terms that weighted sum of the value terms, and you're doing that for each query. And that's what we have in the code basically. So you're doing it for each query, and that's why what you get is NQHD, and you then just pass it through the final linear layer after concatenating it. So that's where we reshaped it. So we had split it here before after passing through a linear layer, and then now we concatenate it again and pass it through the linear layer. That actually completely finishes our self-attention. This was the self-attention block. And I know this took a lot of time, but other blocks are quite easy compared to this. Okay, so let's move to something called the transformer block, but that's basically just a combination of what we've done. Okay. Now, what will be passing through this transformer block? All right, sorry. We will be passing the embedding size, the heads, dropout, and the forward expansion. Now, this forward expansion is just, we'll come to this. You can also keep this 1 if you want. So now this is the attention module of the transformer block, which is what we have already implemented. So you have embed size, and you have your heads, right? Now we'll be adding the layer norms. So I'll show the architecture in the forward. So now let's look at the feed forward that comes after the attention. So you have and it's a linear layer. Sorry, it's a sequential with a linear layer. So the input is the embedding size that we got from the attention block, which is the same as the size that we had from the input directly. Now this is the part where I was talking about this forward expansion. You can keep it the same, or you could change it. The authors change it in the paper, but it depends on how you want to implement it. You could keep this as ReLU, or I would suggest keeping it a GELU, because we've seen that GELU performs better. But that's really a parameter choice for you. You can choose whatever activation you found to perform the best. Okay. Okay. So wait, there's something. This should actually be. And I believe this is the same. But this, let's just clarify the dimensions before. Check dimensions. Now let's look at the forward. And what you're passing to the forward is the, now let's look at the, during the forward, let's look at the block. So for the forward, you'll be passing the keys, the values, and the queries right here. And you'll be passing through the self attention, then the layer norm. You'll have a skip connector, so this is important. Again, passing it through the feed forward that we just wrote, and have a skip connect and a normalization after that as well. And then that's the output of our transformer block. So value, key, query, and the mask. So yeah. Now I'm passing it through the attention block directly. And what am I passing? I'm passing the value, the key, the query, and the mask. Now, after the attention, there's a skip connect, and we also have a dropout. You can, however, not have the dropout. It's completely up to you. So we pass it to norm1, and we add, we add the input here directly, which was the query. That's the, now this X is the input to the next feed forward layer. So now forward, we go to self forward. And again, there's a new skip connect here. So it becomes out is equal to self dot dropout. This is again on whether or not you want to apply one more. Typically, having just one should also work. But that's again based on the applications. All right. So now we will be using this transformer block to create the encoder. So we've already done the multi-head attention. We've done this. We've combined it together with the feed forward. Now we'll be using that to create the encoder. So you have what is the input to the encoder. This is the part where we'll be actually looking at the positional embeddings also, but we will be implementing it in a simpler way. You could use the class that I've defined here as well. Actually, let's just look at this briefly. Although I'm not using it right now for the code, let's just look at it briefly. This is from the annotated transformer blog. And all right, so what's happening here is you actually create the position term using this sine and cosine, which is added to the input, like was so. What's happening here? You have the input embeddings coming. You use the positional encodings and you add them in the passing. It's basically what's happening here. So you have your input x being added to this variable which is generated here, and doing a dropout. So this is, you don't optimize over this, but if you wanted to, you could. So you have the you have this position which is the same length as whatever your maximum length is, and then this div term is the part. This div term along with the sign is the part which actually encodes the information about the position. So this div term is actually created using this using an exponential term which is multiplied with the position. Now this exponential term, I don't want to go too much into the depth because we don't. It'll take some time. It basically what it does is, maybe I can annotate. You have sines of different frequencies. Then you have, this looks terrible, but what I'm trying to say is you have sines of different frequencies, and those actually encode the information of the position. So that is where the sine term and cosine term actually comes in and helps. And the reason you do that is so that, because these terms are actually periodic, when you encode all this information, you make sure that elements which are in the sequence never have the same value. And this idea is actually really useful with some other places. So if you've heard of something called the neural radiance field paper, which is in the CV community, they use this positional encoding for making their network better. Basically, they wanted, whenever you want some, if you have, let's say, two elements which are close together, but you want them to have some, when you pass it to the network, you want them to have some way to distinguish between these two, you could have a positional encoding term added to it that makes sure that even if they look the same and they're at different positions, you actually pass that information onto the network. And that's why this is required. You actually don't optimize over this, because this is just to add information. You don't want to optimize this. This just tells you that these two things are not the same. So yeah, now in the encoder, I think I digressed a bit, but it's useful. So you have the source vocab, right? Vocab size, sorry. The embed size, and the number of layers of these the encoder block that we just created. So we just created those, and let's just pass it to the self. Oh, my bad. There are actually some other terms. Let's do this first. We'll also be passing device the forward expansion term that we used in the encoder block. Dropout and max length. Need this for the positional encoder. So, all right, set of devices decided. Let's go to the word embeddings now. So word embedding. Is now, like I said, this this is the input embedding, and we create this using the vocab size. So this is the first embedding, and this is where we'll use the not embedding function. So you have the source vocab size, and that's why you have number of embeddings. And the embedding dimension, which is the embed size. Let's do this also. So this is just to make it abundantly clear. Now I'm doing a hacky way, but you could use the code that I've added above as well. Let's make it again easier so that again to make it abundantly clear. Why is this not working? Oh my god, yeah, my bad. There should be numbers. And then you have the embedding dimension, which is embed size. What this is showing is basically your word embeddings, the number of embeddings are the vocab size. So like I said at the beginning of this recitation was you have some indices for each word in the vocabulary, and you'll be using those to create an embedding which is random usually. You use those, and the size of those is obviously the embed size that you've already passed as parameter. You use those. Now think of this as the positional encoding that I just explained about, but what you have is you have this max length, and that max length is the number of embeddings you have because you're looking at it in terms of the position of each word. So this encoding doesn't take into account what the word is. It will be, we will be using that later, but we won't really look at what the word is. We're only looking at the position. So that's why making learned, it makes sense that you don't want to keep it. You don't want to learn this parameter, which is fine. You could actually make it true, and there could be ways in which that could be done. And then you again have the embedding size to be the same because you'll be adding the two. Now let's look at the layers. This is for the transformer block. So you have embed size, you have heads, dropout, and you have the forward expansion. These are being passed to the network. Oh, am I not? Okay. I think I missed defining heads here. So you could also have this. This is basically the number of times a transform block will be called. Okay, so this for numbers. So this is basically this self.layers is the number of time you called your transform block. This is all there is. We again add a dropout. And now to the forward there. The input and the mask again. The mask is the part that you move forward. Okay, so you have the n and sequence length equal to shape. Then you have positions equal to now this is for the position. So what we've done here is passing the maximum length, right? The sequence length in this case, and we now change the dimension. And pass it to the bytes. This is the input. Again, passing a dropout. 2. Now we'll be working with the embedding. So you have self dot word embeddings, which depends only on the words. You pass the x plus the self of positional embeddings, where you will pass the positions. So what you created here was a list of which is from 0 to sequence length. So basically that's for each word. And then you expanded it n times. And now you just passed that to the positional embeddings. So that gives for each word comes out with an embedding dimension, and to that we add for that word the location and the size, you add the positional embedding to it. That's all that this is doing. Okay, now let's look at the final part of the encoder, basically. So in this encoder, the key value and query are the same because it's the self-attention, and the decoder, this will change. What we do here is basically now go through all the layers and clear out is equal to layer of out Okay, this is not layers, this is layer. So you have layer, out, out, mask. Key, value, and query are the same. That's why this is happening. So it looks a little weird, but that's what it is because it's the self-attention block. This is the encoder. And all I do is pass now. Just to make it clear what is happening here is you have this. We did the self-attention, we did the feed forward and made the transformer block. Now we're doing the encoder. For that encoder, this is actually stacked on top of each other. So the inputs, the outputs from this one block, you have some output. You pass the same outputs again here, which might seem a little weird, but that's actually what self-attention is. You have the same source, you have key, value, and query coming to the same source. So you have each part in the query actually attending to itself. And that's what self-attention is. I hope that makes it clearer and sort of like a light bulb movement if you had not understood it before. Now, once this is done, we'll be actually passing it to the decoder. However, for the future recitations as well, this would be useful for the future transformer recitations. That will be a useful thing to remember because other variants of transformers, BERT and such, also just use these separately and just work with those because they have a lot of information in them. They use them for different tasks. So yeah. Now let's go to the decoder and the decoder block. Just so if you're tired, just to make it clear, the self-attention part was the only involved one. These others are just engineering, but we would be going to them. We'll still go through them to make sure that we are not, we're clear about the smallest thing in this. What is the input to the decoder block? The input is embed size because again, this is also taking input, heads, forward expansion. I would keep the forward expansion to be 1, but you could change it if you want. So this is actually that transformer block would come in useful because you'll be reusing that piece of code again. So let's have a layer norm defined. For the initialization, I'll not go into the architecture when we come to forward, because it's easier to understand the sequence in which these are called. I'll go into the architecture then. My bad. This is actually sorry. So attention, pass the embed size and the heads. Then you have the transformer block. And to that, you pass the embed size again, the heads, the dropout, and the forward expansion. Okay, I should make this. one more dropout. Okay, now let's get into the forward, which is where I'll explain the sequencing. Okay, so first we do self-attention in the beginning. So you have attention equal to self dot attention, and you pass the inputs, and you pass the mask. So this is something interesting to note here. Let me finish this and then we can look at it. So you have the skip connection, query, okay. Now look at these. Now let's look at this one by one. While looking at one paper. So you have a mask multi-head attention, which is the input, and it's self again. So let's look at this. Hopefully this won't be too bad. Yeah, okay, it's bad. My bad. I'll enlarge it and then we can look at it again. So you have self-attention, you're passing the X again, which is this key value and query. I hate this. Why does it keep going back? And then you have dropout uh, on top of this. So this is the first part, the key, query, and value. Then you have a skip connect, and so you add the X with the attention again. Again, remember we made sure that the dimensions were the same. And then you have a norm and then a dropout. So this is this part. The interesting part after this is you have the cell.transformer block, except now the value and key are coming from before. So that's why if you see what's happening in here in the first cell.attention, what you have is this XXX is actually coming from the output. And so what you have is a training mask, a mask on the input that's coming in from the training data. And now for this part, for the self-attention that you have after the first attention. So now you could actually call the transformer block directly, which is what we're doing, because this is actually the same as this, except the input is now different. So if you remember, this was the block that was for the encoder. You can clearly see that the inputs are the same because it's the same because it's the encoder and you have self-attention all across. In the decoder, the first part is self-attention, so you have X, X, and X. The key value and query are coming from the same data. But for the next part, you have key and value coming from the encoder, and so that's why the key and value are passed, which is what we are sending, and the query comes from what we have before. So this part, the decoder, and so for that reason, the mask is actually the source mask. So for this, the mask is from the source. So it's the source mask. And you just return it. These are the small things which, when you code out, are quite clear. So that's the decoder block. Now we'll make the decoder using the decoder block. So we'll copy some stuff because it's the same. Okay. So just like the encoder block, you have the training vocab size, because that's what we'll be using for the embedding from the training side. The embed size, num layers, heads, number of heads you need for those multi-attention, the forward expansion, the dropout, the device, and the max length. So you have self.layers is equal to the modulus, the way we had for the encoder block, and in here you have the decoder block, and you'll be passing the embed size, the heads, the forward expansion, the dropout, and the device. I mean, this might seem intimidating, but half the things are just trivial. The forward expansion, dropout, and device. All you really care about is the number of heads and the embedding size. That's it. I mean, even those are trivial, really. So let's see out, because you have a linear layer after everything, the same as the encoder. The very cool thing to see here is the same thing actually works for vision as well. We'll look at that in the next recitation, but the same block actually works for recitation. Actually works for vision, I'm sorry. And there is no convolution in there. It's just linears and attention, which makes it very impressive. So you have the embed size and the training vocab size. For the last one, this is. Okay, now in the forward, I'll go through each part again, just so it's clear. Right. Okay. So what do we have here? We have n comma sequence length. The same way we did it for the encoder, really. So I'm just repeating that stuff, because the only thing that has changed here, it's the target vocab size, which you'll be looking at. Right. So now you have okay. Again, like before, we're just adding the position embeddings now. this is cross retention. So I'm just going to copy what we did in encoder again, which is for each layer. You have the encoder, right? So because it's cross retention, you can see that your queries are from what you have coming from your the queries are basically what is coming out from each layer, right? So this layer outputs the query, and that query is again passed, and the key and value are actually the encoder outputs. Now, finally, after those n times, those are done n times, you pass it through the linear again, and then you return. Let's look at it again, just so that we're sure. So we looked at this, which is we have the self attention here for each query, and then after that we have this query and the key and value coming in from your encoder, and this again the transformer block that we've defined already, and this entire block, the decoder block, will be run n times. That's the decoder. So that's what we have done in the code if you look at it. So you have this decoder, and in that decoder you have the X, which is the input coming in. The encoder out actually acts as the key and value, but that's only during the cross attention part. So you have the n sequence length, the positions, and then you create the position embedding just like you did before. Now you actually pass it through the decoder multiple times. That's why you have for layer and self layers. There is in this entire thing, this block will be stacked on top of each other. So you have that X coming in, that X actually is doing self attention on the masked multi-head attention that it has, and the encoder outputs are passed here again, are passed along with the X here again. Interesting thing to note here is the encoder output is the same. So you're really passing the encoder output the same across all these layers. So for the first layer, the encoder output is the same. Again, the X changes, the encoder output is the same. The X changes, the encoder output is the same. Your X, which is the information that you're getting from your output, is what is changing. That's it. And then you have the final linear layer and you output it. Okay. We can now, and again, this is of training vocab size. This is interesting because you're doing next word prediction. All right, so now we combine the encoder and the decoder to create a transformer. This is the finale, the part that we've been waiting for. So now combine the encoder and the decoder. Now what do you pass here? Pass the source vocab size, the training vocab size, source pad index, the training pad index. This is I'll look at this again once we are in the forward. This is just so that we know what all are we passing. So the embed size, we take it to be 512, can be increased or decreased depending on how much you want to train. So now layers, 6, forward expansion, 4, I would keep it 1. Let me just make it 1. Or just for the paper's sake, let's keep it 4. Okay. Now again, the encoder the same way we had defined before. Pass the source vocab size, pass the embedding size, pass the number of layers. It's now at this point it's trivial. We just have to pass all the parameters, and the good thing to notice here is what this parameter really means in the grand scheme of events, um, because that would actually help kind of make it clearer in your head how many components there are and how each small thing is connected to the entire transform. The income size, the member size, layers, and forward expansion, dropout device. Max length. You need that. Okay, so now we have the encoder and the decoder defined. We'll be calling them in the forward. What we have, I'll go through all this in the forward again. That will make it easier. Right. So now, okay, there are a bunch of functions that we want to look at here right now, because those are the ones that we've been till now passing but not really looked at, which is the mask. How do you create the mask? So there are, let's look at that, and then we'll tie it all up in the forward. So you have to make source mask, which is which takes in self source, and then you have source mask is equal to the, now if this is where the indices really come in. So when the source is not equal to the self dot source that indices, you have the mask, right? So I'll again go through this in case this is not completely clear. So the shape here is now, and because we unsqueezed it twice, that will also become clear why have we done that. uh, okay, I can actually just say that right now. It's because you multiply the mask with the input, and you need them to be the same dimension. I mean, in this case, it's not the same dimension, but it'll broadcast. Okay. So you have your padding indices, and the parts where it's okay. So here's where the source mask comes in. The source mask might have different lengths, and you have now padded this. This is also quite important for homework 4 where you have the same scenario. So the parts which are padded, you don't want to include that. So this actually makes it 0 at the parts where you don't have you have um okay, let me put it this way. This will actually 0 out the parts where you have padding. That's what it does, so that you only take the parts which are important to you. This okay. Now the training mask is the mask that we've been talking about till now, which is you have um let me show it. So then once I write the code and after that we look at it again, you have this triangular mask. That's what we're trying to create now, which is so that you have this part where it only attends to the part which are parts which are um, before it. So training mask is actually self-taught. Sorry, it's actually dot. This is the triangular. It takes. This is not quite straightforward. I mean, it is straightforward, but um, I would suggest looking at the documentation. That would help you completely understand what's going on here. So you basically just created a triangle. You've just created a square, but half of it is yeah. The best part for this would be to actually just look at um, the documentation. Yeah. Now again, just the way we did it before, we want it to the same shape because we'll be multiplying it as the input. Now we have this, and we will be returning it. So return I have done that. Not sure why it's not sure. Okay. Right. Now the final part where forward where we look at it again. So you have the source mask, you have it equal to Okay, we created the masks the way we had done before, where the training mask is the one which is triangular because you don't want it to see the values that are in the future, and the source mask is the ones where you remove the padding indices. So you have now I can actually call the encoder and the decoder. So you have the source and the source mask. And then you have the decoder. So basically self dot decoder times basically the training decoder source. So this is again cross attention. Remember that this is cross attention. So the TRG training is basically the input to the decoder, and then both the source mask and the training mask. And now we return. Oh, and that's it. We are done with the. Okay, there's some error somewhere. I think I'm missing a. Yeah, I think I'm missing a. Yep. So that works. So that's it. This is the transformer. There might be some errors here, but this is mostly it because of coded on the fly. This is mostly it. Uh, it might have seemed a little long. I'm not sure how long the video is. I'll have to cut some parts maybe. Might have seemed a little long, but this was sort of necessary because of the things that I will explain in the next recitation. Because we know these things now, it makes it a lot easier to understand and appreciate the different parts of the transformer in the next recitation. So because we'll be using different parts of this and how they all come together, it's quite impressive. Yep. All right. See you guys in the next recitation.